Okay, Ji. So, can you hear me?
Yes, sir.
Okay. We will start in a minute. Okay, Ji, so that people can join. Okay, Ji. So once we have this situation that the once we have this situation that the PN junction diode is connected in reverse bias, and in that condition, what happens that the free electrons on the N side, they are being taken by the positive terminal and they are being injected into the P side, into the valence band over here, right? And once they are being injected into the valence band, so this means the free electrons which were being taken from the N side, they are injected in the valence band on the P side. So this means the electrons will be moving from one hole into another hole, right? Like this. And eventually the holes will be seems to be moving away from the junction, right? So what will happen that the impact of this will be that the energy hill will be getting more in size, or the size of energy hill will be expanded, because the level of the conduction band free electron, they will be losing its energy. So this means the level of conduction band is reducing in energy. And once it is reducing in energy, so this means they will drop down. And so this means the P side conduction band and the N side conduction band, the gap is going to increase. This means the size of energy hill will increase. And once this will happen, so eventually what will be the impact over here, that we say that the width of the depletion region is going to increase over here. Or as you can see, the electrons, they are moving in this direction. So this means more ions, they will be created on this side, right? And when more ions will be created, so this means the size of the depletion region is going to increase on the N side, as well as when these electrons, they come and they will join over here. So this means the net negative on the P side is also going to increase. So this means the negative ions, they will be created on this side as well, right? So this means whenever the diode is reverse biased, the width of the depletion region is going to increase. The width of the depletion region is going to increase, right? And due to that, what happens that no majority carriers can cross the depletion region. Are you with me? Right? So this means there is no current which is flowing due to the majority carriers. But are you with me? बात
Yes,
समझ में
sir.
बात समझ में आ रही है जी?
Are you, sir?
Okay, so once this will happen, so there will be no current which is flowing due to the majority carrier. But what about the minority carriers? So if you see, we have some of the minority carriers over here as well. And the minority carriers over here are due to the reason of electron hole pair creations. Are you with me? Right? And if you see, this is the negative side, this is the positive side. So this means on the P side, we are applying the negative potential over here. And this negative potential and the minority carriers on the P side, which are the free electrons, they will be repelled. Once they will be repelled, so what will happen? That these free electrons in the conduction band on the P side, they will be just pushed down the energy hill. Right? And due to this, what happens? That a very small current is going to flow due to the minority carriers, because the amount of free electrons on the P side is very, very small. It is only due to the electron hole pair creation. And depending upon the number of minority carriers on the P side, there will be a very small amount of current that is flowing due to the minority carriers, right? So as you can see, this small minority carriers will be just producing a small current in the opposite direction. But the amount of this current is very, very small, right? Question? Anyone? Are you with me?
Yes, sir.
Yes, sir.
Question तो नहीं है जी?
No, sir.
Okay. So due to this, what happens that we have no current due to the majority carriers, but a very small amount of current due to the minority carriers, right? But in case if the reverse voltage is getting too much high, right? If we have the reverse voltage is getting too much high, so we can go into a situation that is normally called an avalanche situation. An avalanche situation arises in the reverse breakdown region. And what happens that if the voltage is increased so much that the free electrons, they get so much excited on the P side that they get into the valence band and knock down the electrons from the valence band. And if they are getting that much energy, they go into the valence band, knock down the only 2 electrons from the valence band. So this means a chain reaction is going to start. That if every electron gets 2 electrons from the valence band, so this kind of reaction will start. And if this kind of reaction will start, so this means a very high amount of current will be start flowing due to this very high voltage, right? So in case if that happens, so a kind of avalanche will occur. You know what is avalanche? Anybody? Have you heard about it? Avalanche.
Yes, sir. I think it's means या इसका
जी
सर ये तो वैसे एक बर्फानी तोदे का ना कहते हैं एवलांची
एवलांच बर्फानी जब वो आप कहते हैं ना कि जब पहाड़ों पे बर्फ
Yes, sir.
पड़ जाती है और थोड़ा सा भी कोई इस तरह का इम्पैक्ट आए कि बर्फ जो है वो पहाड़ उसको रोक ना सके, तो बर्फ जो है वो नीचे की तरफ आना शुरू हो जाती है और वो बेसिकली एक ट्रिगरिंग पॉइंट होता है जहाँ से वो एवालांच आ जाता है। तो वो फिर बड़ा बड़ा नुकसान भी कर देता है। जब आप हिली एरियाज को देखें तो वहाँ पे कभी कभार इस तरह हो जाता है। So the same kind of impact might occur if the voltage is increased so much in the reverse direction. So if that happens, then this means if not proper care is being taken, so this can actually damage the diode permanently. And some of the diode, they are being constructed for the avalanche, to cater the avalanche. And one of the diode which actually works in the reverse breakdown region, that is called zener diode. Zener diode, right? So the zener diode is specifically characterized to work in the reverse breakdown region. Reverse breakdown region, right? Okay, we will see zener diode later on. So I want to just give you the idea what can happen and how we can actually take care of this thing, right? So this is something about the reverse biasing. Any question up till now? Question? Is this thing fine?
सर
Ji, question.
सर मुझे ये एवलांच ब्रेकडाउन और जीनर में मेन डिफरेंस का पता नहीं चला।
ओके, जीनर डायोड जो है वो डायोड है जो स्पेसिफिकली बनाया जाता है, कंस्ट्रक्ट किया जाता है ताकि आप जो है रिवर्स ब्रेकडाउन रीजन में आप काम कर सकें, उसके लिए जीनर डायोड। एंड वी विल डिस्कस जीनर डायोड। जीनर डायोड इज अ सेपरेट टॉपिक। वी विल डिस्कस कि जीनर डायोड पूरा हम उसको इंशाल्लाह पूरा देखेंगे, ठीक है जी। बट आई जस्ट वांटेड टू गिव यू द आइडिया व्हाट इज हैपनिंग इन द रिवर्स ब्रेकडाउन, ठीक है जी। Question?
नो सर।
Okay, ji. So now if we take a look of diode itself, so we have basically voltage current characteristics for forward bias. So what can occur when we make the diode forward bias? So what will happen to the voltage and what will happen to the current, and how we can actually draw the curve between voltage and current. So now let's see that if we have connected the diode in the forward direction, so what we say, we have the forward voltage VF and we have the forward current IF, right? So first, when we increase the voltage across the diode, and before, if we say the diode is made up of silicon, and before the 0.7 volts, what will happen that there will be a very small amount of current that will be flowing, or we can say it is next to negligible before the 0.7 volts, because once we have not crossed the barrier potential, so this means almost no current is flowing. Once we are getting to the barrier potential, after that there will be a very large amount of current that will be flowing across the diode, right? So the curve will be something like this. If you see, let me just redraw it. So the curve will be something like this. Right? So the curve will be something like this. That before 0.7 volts, there will be a very small amount of current. But after 0.7 volts, once we have overcome the barrier potential, then a large amount of current will be flowing. So if you see, if we take the potential before, if we say that if this is the change in the voltage, if we say this is delta VF, right? So what is the change in the current? The change in the current, we say this, right? So this change in current is, we say, delta IF. Are you with me? Delta VF to delta IF, right? Before 0.7 volts. And if we check the change in the voltage after 0.7 volts, so if this is the change in the voltage, this is the change in the voltage. So what is the change in the current is this. This is delta IF, right? So if you see the change in the voltage before the knee of the curve and the change in the voltage after the knee of the curve. So if we take the variation in current and voltage before the knee of the curve and current and voltage after the knee of the curve. So let's say if we say it is delta VF1 to delta IF1 and delta VF2 to delta IF2, right? So this means that if we say delta VF1 divided by delta IF1, right? So what is this quantity VF by IF? Anybody?
Resistance, sir.
Okay.
Resistance.
Yes, this is the resistance of the diode, right? We can say this is the resistance of diode which is being offered before the barrier potential, right? So
Yes, sir.
if you see the other, which we say it is delta VF2 by delta IF2. So this is the resistance of diode after 0.7 volts. And this is before 0.7 volts. Are you with me?
Yes, sir.
Yes, sir.
Okay, ji. So if you see
Yes, sir.
the resistance which is being offered before 0.7 volts is pretty high as compared to the resistance after 0.7 volts. Are you with me?
Yes, sir.
So what we can say that the resistance is changing its behavior before the knee of the curve and after the knee of the curve. ठीक है जी? So once it's changing its behavior, so this means this is not a constant it's not a constant resistance which is being offered by the diode itself. So its behavior is changing. So this means the resistance of the diode is not constant, but it is dynamic resistance, right? Are you with me? So therefore, the resistance of the diode is normally called RD, where RD is basically the dynamic resistance. Because before the knee of the curve, it is very high. After the knee of the curve, it is very low. So what we say normally, that the resistance which is being offered by the diode is dynamic in nature. And once we take a look of the diode in the reverse direction. So in the reverse direction, what we have VR and we have IR. So normally what we have seen that once we increase the voltage in the reverse direction, there is almost negligible amount of current that is flowing due to the minority carriers, right? So this means almost no current or very small amount of current is flowing due to the minority carriers. But once we crosses the reverse breakdown region VBR, so what happens that a large amount of current that starts flowing in the reverse region, right? So again, the curve shows that we have the curve something like this, that again initially it has very high resistance, but if we overcome the reverse breakdown region, the resistance getting very low, right? So it is then it is behaving as a short circuit. Are you with me? So if we complete the curve over here for the VI characteristic curve, so what we can say that the complete curve will be something VF, IF, right? So the curve will be something like this at 0.7 volts. In the reverse direction, it will be something like this at the VBR, and this is VR, and this is IR. Are you with me? Are you with me?
Yes, sir.
Yes, sir.
ठीक है जी? Any question up till now?
No.
Okay जी. So now, because this is the behavior of the diode, and in electronics, as you can see, the behavior is not constant. So what we need to do, we need to actually, in electronics, we need to use some kind of models so that when we are dealing with diode, because the behavior of the diode is not constant every time, it is changing. So to deal with the diode, what we need to do, we need to actually model the diode in such a way that we can use the diode in electronic circuits, right? So for that, we have actually come up with different models of the diode. Now, there are basically three models which are available. So the first model is called the ideal equivalent model or ideal equivalent circuit for the diode. Now, how we are actually dealing with that? So there are basically three models or three circuits which we normally use. So we say, okay, models slash circuits. So the first model is called ideal equivalent circuit or model, right? So in this, what we say that the diode is actually behaving as a short circuit thing, right? So if we have a diode, so what we say that if the diode is forward bias, the diode is forward bias, so what we say, the diode will be behaving as a short circuit switch in the forward direction, right? So the short circuit switch is like a switch which is being closed, and that is our ideal case, right? So in that context, what we will say that the characteristic curve will be something, we say this is VF, VR, IF, and IR, right? So this means whenever something is short circuited, what is the voltage across that thing? Anyone?
Zero, sir.
So if we are considering the diode as a short circuit switch, so this means the voltage across the diode will be taken as zero, right? So when it is being taken as zero, so the short circuit thing will be having a curve which is starting at the origin. Are you with me?
Yes, sir.
ठीक है जी? And when we are considering the diode in the reverse direction, so if we are considering the diode in the reverse direction, so what will happen that we say the diode is reverse bias in the ideal case. If it is reverse bias in the ideal case, so then the diode will be behaving as an open switch, right? So the ideal case, the diode is behaving as an open switch. So when the switch is open, so this means no current will be flowing through the ideal diode. And once no current is flowing through the ideal diode, so the curve, we can say the curve, this means this is a flat curve over here. Are you with me?
Yes, sir.
ठीक है जी?
Yes,
So
sir.
when no current is flowing in the reverse direction, this means the whatever the voltage which is being applied, it is all applied across the diode itself. Right? So this is basically the VI characteristic curve for the case when the diode is being considered as an ideal diode. Right? Okay, ji? Question? Any question?
No, sir. No, sir.
Okay.
No, sir.
Now, the second model, which is there, it is called simplified equivalent model, or it is also called practical model. So let's see that. Right? So in that case, what happens? That in the practical case, what we say, that whenever the diode is forward bias, whenever the diode is forward bias, so it is being taken as that we say that in the practical case, we say that there is a potential which is equal to barrier potential, and that is actually our VF. And then there is a switch which is connected in series to that of the VF. Are you with me? And if it is made up of silicon, so this means VF is equal to 0.7 volts. If it is made up of germanium, it is 0.3 volts, right? Are you with me?
Yes, sir.
ठीक है जी. So when we draw the VI characteristic curve, so it is going to be something like this. We say VF, IF, VR, and IR, right? So this means that at 0.7 volts, we will have a curve. Till 0.7 volts, no current is flowing, but at 0.7 volts, we will have a current that is flowing in this way. So this is our practical model, right? And in the reverse direction, again, it is behaving as an open switch, which we have seen in the ideal case. So this means in the reverse direction, it will be something like this, right? So this means, again, it is behaving as an open switch. So when it is behaving as an open switch, so it is same as in the case of the ideal case, right? So it is behaving as an open switch. So when it is behaving as an open switch, so we have a curve something like this. Are you with me?
Yes, sir.
Okay, Ji.
Yes, sir.
So the third model is called the complete model, or it is also called the piecewise linear equivalent model. The third model is called piecewise linear equivalent model. Now in this one, what is happening, that whenever the diode is forward bias, so we say whenever the diode is forward bias, so it is being taken as the 0.7 volts, then we say we have a resistance which is normally called RD, and then there is a switch which is being closed and it is connected to biasing voltage, right? So over here it is 0.7 volts. Then we have an RD which is connected in series, and then there is a switch which is being closed, right? So in that case, what is happening, that the VI characteristic curve will be something, we have VF, we have IF, we have VR, and we have IR, right? So this means till 0.7 volts, we have no current which is flowing. So it is something like this. And after 0.7 volts, we have a curve something like this, right? So it is the slope due to the dynamic resistance. Are you with me?
Yes, sir.
ठीक है जी, जो ओम्स लॉ की स्लोप होगी वही यहाँ पे आपको स्लोप मिल रही है आफ्टर 0.7 volts. So this is basically the
तो
piecewise.
ये भी टेम्परेचर डिपेंडेंट होगा सर?
जी ये टेम्परेचर डिपेंडेंट होता है, बिल्कुल होता है. तो जब रूम टेम्परेचर से ऊपर होता है तो इसके कर्व की स्लोप चेंज होती है, राइट?
ओके सर, थैंक यू. यस सर.
ठीक है जी. ओके, so when we take a look in the reverse direction, so what happens, that it can be taken as an open switch, but at times it is also being taken as an open switch in parallel to a very high reverse resistance, so which is normally called RR, reverse resistance, and it is being connected in such a fashion that the diode is reverse biased, right? So when there is a very high reverse current in parallel to an open switch, so this means a very, very small amount of current that will be flowing. So the curve will be something like this. Previously, the curve was just parallel to the horizontal axis, but now as you can see, there is having some slope in the curve. And that slope in the curve is due to the very, very high reverse resistance, right? So this is basically the VI characteristic curve for the piecewise linear model. Are you with me? Okay, Ji, the session is going to end less than a minute. If you want to have any question, you can ask me, or we can start a new session afterwards. Question है तो पूछ लें.